So, as we all know that artificial intelligence is growing exponentially. There is no doubt about that, right? So, self-driving cars are picking up millions of miles. Then IBM Watson is the diagnosing patient better than the armies of doctors, and Google DeepMinds, which is nothing but AlphaGo, beat the world's champion at Go, a game where institutions plays a key role, right? So, but the further AI advances, the more complex become the problem it needs to solve, right? So, and only deep learning can solve such a complex problem, and that's why it's now comes into the existence, right? So, basically, today we are going to start with this particular concept which is to be there in our syllabus. This is one of the most advanced algorithm, right? So that is one of the most advanced algorithm that exists in the world of super supervised deep learning. So let's get started. So we have our little brain, little thing we have done of the supervised versus unsupervised deep learning branches, right? So, and here we are got to artificial neural network, which we have already talked about. So we have already talked about the convolution neural network as well, and today we are talking about the recurrent neural network. So this is just so that we see where we are in the big picture of things slowly getting to the unsupervised part of the course. But let's focus on RNN in today's session. So already, so now that we know where we are and on these particular things, we have to understand the condition where why are we doing this? That is the most important question we have to understand, right? So why we are looking at the human, why we are considering here the human brain as if it's just map of the world, right? Well, the reason for that is the whole concept behind the deep learning is to try and mimic the human brain and get that kind of similar functions as the human brain has, and the things that evolution has already developed for us. And I thought it would be pretty cool if we could somehow link the different branches of deep learning that we have already discussed on, or we can consider the algorithms that we have already discussed. So we'll talk about the ANN, CNN. Now we are talking about the RNN, and if we could link those to some part of the human brain, and if we all make sense. So let's have a look over here. So we have got the brain, the human brain, and it's got basically three part, right? So we have got the cerebrum, where which is all this colored part, and then we have got the condition which is understand, which is considered that's the little brain, right? So actually look at it up at the Latin that is to be considered over here. That does means little brain. Yeah. In this particular part, we are talking about ANNs, that big orange picture where we can see all of those little neurons everywhere trying to find or gauge how many there are, considering the millions of neurons in the brain. And then we have got the brain stem over here, which connects to the brain of the organs and our arms and legs and so on. And so those are the main three parts of our brain. And now the cerebrum has four lobes, and they have color is considered over here, right? So we are considering here optical lobe. You can see in this particular picture where you can consider. So we got ANN. We already discussed about CNN and now, and the hardest one was the probability to start off with ANN, because with the main advantage of ANN. Well, so the main advantage, the main breakthrough is NN is apart from the back propagation algorithm, which kind of applies to all of them, and in fact whatever applies to the NN applies to everywhere here. So considering here this particular part where we have to learn through prior experience and through that particular prior impulses and through prior observation, that's extremely valuable. And so that's do those with those weights represents over here. And moreover, the weights of the codes are present across all the neurons in the brain. But we are going to try to make away the main psychological, or you can consider underlying the particular part, where we have to consider that the weights represent long-term memory, right? So that once we have run the run the ANN and train it, and then afterwards you can switch off, you can come back like, right? So it's train up and you come and you know the weights, and so where input you put into it, it will be processed, and it the same way as it would be considered in the last time, right? So which were the consider the part of the second part also, it will be consider the bits or the long-term memory of the neurons, and that's the why bits are considered over here. So here we are considering the temporal lobe is responsible for long-term memory. Then afterwards, the consideration over here, the brain is very complex, and the other parts as well responsible for memory as well. But we are going to simplify the things over here. Maybe we have to consider the temporal lobe. Then the CNN is the much easier. It's version recognize of the images and objects and so on. So we are having optical lobe over here. So let's consider this point where we have to go into this particular diagram where we have to understand this part, right? So in this particular part, if I want to understand the optical lobe, then we have consider here the main important what exactly remembering things what just happened in the previous couple of observations and apply that knowledge going forward. So here I'm going to apply. I'm going to always consider here that here that the rest of the uh, consider here the most important thing is frontal lobe, right? So that's where have a lot of short-term memory, and of course the frontal like a quick breakdown. So the frontal lobe also is responsible for personality, behavior, motor cortex, working memory, and lots of the things, right? So, but with the other purpose, the main thing that we are looking out for the shortest memory, right? By the way, so if I consider if you are considering the temporal lobe is concerned with the recognition memory, that's our long-term memory. Then partial lobe, and these are the forms of considering the Wikipedia over here. I can get this particular image from the Wikipedia, and partial lobe is responsible for sensations and perceptions and constructing the spatial coordination system to represent the world around us, right? So, and we are yet to create a neural network which would fit into the category, and occipital is a version. So although so there we got a bit of neurosciences. So let's move on to our favorite neural networks, which is to be considered here in this particular part. So let's move to that particular network where we have got a simple artificial neural network, three inputs, two output, and one hidden layer. So what does an RNN do, or what does or how do we represent or turn into an RNN? So we have to consider here. So they are still there considering here that if we are looking for under earth, or we can consider this neural network, so we are looking into the new dimension. So it's still there, it's just flatten out, we are adding a new dimension to all of this. But remember that those neurons, the work, whole network is still there, nothing changed. So we just squash it for our purpose. Then to simplifying the things, we are just going to change these multipliers into two. Then we are gonna twist things, whole things, make it a vertical, because that's the standard representation. And then it's and in terms of neural matrices, we are gonna color them, right? So instead of green, we are gonna color the hidden layers in a blue, and then consider over here in this particular figure. And the line is temporal lobe, and this is the and consideration over here that we are that means basically means that this hidden layer not only gives an output but also fits back into itself. So again, if I am going to consider here what exactly that circle, that there are still considering we are just focusing on what we just remember, that each one of these circles is not one neuron, it's a whole layer of the neurons. And so what is happening is you have input coming into the neurons, they then you got outputs, but also the neurons are connecting to themselves through line. So that's the whole concept, that they same some sort of the memory, short-term memory, and they are remembering what was it in the neuron, just what we have previously done. And then before that, it is just remembering what is the previously, and that allowed them to pass information on to themselves in the future and analyze things, right? So the kind of like when you are watching this particular part, or you are watching the particular course, it would be very sad if you could not remember or what was happening in the previous tutorial or previous session, right? So if even if we break the time down discretely through, not by seconds but continuously by seconds, by discretely through this particular session, and we say like every moment in the time is new session, it would be very sad if we did not remember all and what we had done in the previous session, so in the previous section or in the previous part of this particular course, because this whole neural network part would make any sense. So you wouldn't have memory of what a neuron is, what an activation function is, but because you do remember those things, you can understand this particular part very clearly. So same thing. So why we consider this particular artificial construct, which is supposed to be synthetic human brain or mimicking the human brain? Why would we be considering this part? Because something so powerful as a short-term memory. So long-term memory great, but short-term memory is so powerful, that's why it gives the opportunity, right? So and that's where the recurrent neural networks comes into the picture, and that's the gap that they fill into this particular part. So let's understand with the example and image where the computer describes the image. So you can have one input, the image, and it could be going through the CNN, and then it would be fed into the RNN, and then the computer would come up with the word to describe the image, and in this actual computer describing the image. So how accurate it's that black and white dog jump over the bar, right? So this is a computer that looks at this image and it was like, oh, it's a black and white dog based on what it's previously learned. The long-term memory, it allowed it to come up with a bit and come up with the certain features, recognition system, and come up with the filters, come up with the everything that is required in a CNN. And then the RNA allows it to make sense out of the sentences. So you can see that the sentence actually flaws. There is an consider over the bar or over this particular verb, that's a noun, and so on. So basically, RNN is what allows it to put a sentence together in this particular case. Then many of considering this particular example where we have to convert one language into the, or we want to translate from English to this particular Spanish language, or this particular language is to be mentioned over here. So this is all about consider as an example of Google Translator. So the translator uses RNN or not, I know that they're very sophisticated deep learning Google Mind, and I have heard that they have used that in their Android system and so on. And I'm not sure that if it uses RNN here or not. So, but the concept is remains same. So if we are considering this example, converting this English to Spanish, then there is to be considered basically the other languages, what other language is important. So what gender you a person considering, oh here it is a male, it is a boy, it is a female, like that. So that's why it's got that particular thing. Then if it is changes that particular gender, then what it comes into that particular language. So that we have to understand in this particular part where it does know if the Google Translate uses an RNN. So I'm considering that part. Basically, the concept is the same. That's you need to short term information about the previous word in order to translate the next word, right? So you can't just translate word by word. And it's just a simple example of this particular session where I to make a sentence, make a sense. You do to consider the need the information about the previous word, right? About very visual example. This is example that I am mentioning right now. So this is all about taking the consideration over there. The RNNs have power because they have a short-term memory and they can do the things very easily. In this particular example, it has been related to the considering the images. There can be lots of and lots of different applications of RNNs. For instance, many to many you can use RNNs to subtitle the movies, meaning that you can have running subtitles or describing every single frame in a movie, and that is something you can't simply do with the CNN or other neural network, because if you are watching a movie, you need the context, right, about what happened previously to describe what's happening now. And so you need that short-term memory. So you can't just run through a million movies and kind of understanding that whole plot that is going to happen. So you need short-term memory of the plot to be able to comment on a single frame, right? This is basically one another example I have mentioned over here regarding the considering the RNN, that is basically an LSTMs has to be specific over here. So I'm going to show you this movie just because of considering this particular part, that how they have used a particular part for this particular title, where they have used the algorithm turns out by hilarious, and it is not describing properly what exactly he is saying. So this is the one type of application basically you can consider here. So the name is mentioned over here. You can just go through this particular document where you can understand what exactly or how exactly they have done the great job. But uh, amazing, it does look amazing in the end, but you will notice and kind of look out of for this when you are watching the separate the sentence, and you will see that each sentence on its own more or less 90% of them makes sense, but overall it can't probably link sentence together. And that's the next step for RNNs. This is still quite a new technology, or it's only picking up the recently, so it's be developed very soon. It is not yet full-fledged developed. And maybe when you are watching this tutorial, you are laughing also because of this particular part where it's saying that already, considering that particular part where it is not trained properly. So highly recommended checking this out, only 9 minutes long, right? So there you go. That's the RNN is nutshell. And then in this particular part, you have to understand what exactly the RNN is. So in this particular part, we have to understand in today's session where we have understood the huge problem that exists with the RNNs. All right. So what is this problem called a vanishing gradient? It was the first discovered by the Sik Hochiter, and I hope this is the actually the correct pronunciation I have done, because it's very interesting over here. So I know we have a student from this particular Germany, and so you can comment on if the particular part where we have to understand this particular consideration over here. So he was much younger, the person who has just now I have shown in this particular PPT, when he is actually came up with this concept. He found that there was a big problem, and we will talk about the problem itself just now. And I just wanted to point out who are the people that spotted this. And basically, as you will learn from the future tutorial or future session, that is used by the this particular modern way that we use RNNs and LSTMs, and we will talk about the future down. But this consideration over here that just want to make sure you know that what exactly all about this particular part. And the second person is Bengio. He is a professor at the University of Montreal. He also discovered that this problem, and I think a bit later in 1994. So SIPA was discovered in 1991, where he has wrote about the consideration over here, and Lucia wrote about this in 1994. But again, this is another person driving this whole, pushing the envelope in a space of RNAs. And if you go through the University of Montreal and you look this particular professor's profile, you will find that the Yoshuna has over 500 research papers. And by the way, there is Benjio just hanging out with this programmer, and you can see here all of each other. So it's very thick night community basically. So let's understand the idea, quick idea of who is behind of all of this. And today we are going to continue proceeding to the vanishing gradient problem itself. So as you remember, this is the gradient descent algorithm. We are trying to find the global minimum of the cost function, and that's gonna be the optimal solution, optimal setup as for the neural networks. So we can recall that as a gradient, right? So all your information travels through the neural network, and you can find out this particular part. And we have got some weight written out, right? So what happens if the recurrent neural network is similar things, but here you have got a bit more going on, right? So when your information travels through the network, it travels like that, right? So you have got lots of travel through the time and information from previous time points goes. So keep coming through the network, and remember that every node here, it's always very important to remember for neural network that every single node here is just a node. It's a representation of a whole layer of nodes. So remember, we were looking at form from the top of, or from the bottom. They are actually extend through this particular chart, where down into this particular part, where we had to consider the lots of more neurons behind the one that we can actually see, because each one represents a layer. Very important to remember that. And so at each point in the time, you can calculate your cost function or your error. So basically your cost function compares your output, which is in the red circle, and red circle to your desired output. So to what you should be getting, and this happens during the training. And so, and you have these values for throughout the time series. So for every single one of these red circle, you can calculate the cost function basically, and it's focus on one just to understand what's going on. So let's focus on this one specifically at time t. And so you have calculated the cost function, which is t, and now you are want to propagate your cost function back through the network. So well, how it's going to look, because you need to update the weights. So every single neuron which participated in the calculation of the output associated with this cost function should be, or should have their weight updated too, in order to help in better calculation the output to minimize that error. And the things here is that it's not just the neurons in directly below this particular T, directly below this particular red circle. So it's all the neurons that contributed, and there are many more of them. So there is all of these neurons as far back as you go. So depending on how many times steps you take, you might take one time step, you might take two times, or you might take 50 times steps, depending on how you set up your network. And this is where the problem lies, that you have to update, or you have to propagate all the way back through time to these neurons. And when we talk about time, it's not that the problem is that we can't travel through time, not at all. So we have considering this particular network, where so this whole propagation can be facilitated. The problem lies in something else, and as much as I don't like putting math on the slide, on the this particular slide, I have added some point of the maths, but I will consider out one thing here. So the math behind the arrangements, and we will definitely directed you to that particular additional reading which you want to require to skill upskill or on this particular math concept. So here we have got WREC, and WREC stands for weight recurring, and that is the weight that is used to connect the hidden layers to themselves in the untold temporal loop. And as you can see here on the left of this particular part, in order to get from minus xt minus 3 from this layer. So 2 you need to apply WREC, right? So then from here you from here to here apply WREC, and in simple terms and intuitive terms that you are doing is you are simply multiplying the values here, are you are remembering to get from the layer to the next. So we multiply the output by the weight, and then we get to the next layer, and then we multiply the output by the weight and get to the next. And when we multiply the output from here by the weight, you get this particular part, right? So by the same exact weight multiply times many times, or how many times you are going to go through this particular temporal loop, and this can be set. So this can be set this particular network. So do you wanna do it once, or do you wanna look back one step, or do you wanna back 3 steps or 50 steps like that? But as many times as we do it, we have to multiply by weight. And this is where the problem arises, because when you multiply by something small, your values decreases very quickly, right? And this multiplications comes from this p here, whatever we are considering that particular part. So xt to xt minus 3, and that is exactly p stands for multiplication. P in this p stands for multiplication, so we have to multiply, and that's what it's representing. That's as far as you go back to your multiply, and as you remember, weights are assigned at the start of your neural network, and you see in the this particular practical session, if you want to consider, your weights are assigned at a random values, but the random values close to 0. And from there, the network trains them up and identifies what they should be. But if you start with random double or random WREC close to 0, then because you are multiplying by it many times, by more you multiply, the lower the value gets. So if you start off, you might have a certain gradient going through your network, being back propagated through your network. Then you move backwards and your gradient becomes less. Then your gradient becomes less, then your gradient becomes even less. And what does that means for this particular network? And this is important part to consider here, that what does a vanishing descent like that, why it is bad for the network? Well, because the gradient, as it goes back through the network, it is used to update the weight, and we know that already. So well, the lower the gradient is, the harder is the network to update the weights. So it cannot right? So it can still understand what kind of contribution each of these output has towards the error, and therefore it can update the weights. But the lower the gradient, the slower it's going to update the weights, and higher the gradient, the faster it's going to update the bits and get you this particular final result. And so therefore, if you have, for instance, 1000 epoch, then these bits for this layer might be updated towards the end of the 1000, and you will have some final results. But these bits, because the gradient so much smaller, they are gonna be updated slower, and therefore by the end of the 1000 epochs, you might not have a final result there. And therefore, this part of the network is trained. So this part of this neural network is not trained based on the cost function. But the problem here is not just the half your network is not trained properly, but also that these weights of these layers, its outputs are being used as input for the further layer, right? So the training here has been happening all along based on this base of inputs that are coming from the untrained neurons to untrained layers. So it's kind of a viscous cycles basically. So you are training here and you think you are getting good results, but because your gradient so small here, this is training so slow and the output is giving is so incorrect, right? And not final output. And therefore you are training on the non-final output. So because of this balance, because of vanishing gradients, you have a problem in your network, which is not just that these weights are not being trained properly. The whole network is being trained properly because these weights are not being trained properly. And that's, there is like a consideration over here that whenever you look into the network, always the ones at the very back are going to have that problem. And this is the nutshell what the vanishing gradient problem for the recurrent neural network is. And that's that's was the kind of the main roadblock to using recurrent neural networks. And let's consider summarizing all these points in the short form. So we have, if WREC is small, then you have a vanishing gradient problem. If W is large, you have an exploding gradient problem because same thing, but then it's just gonna explode. And here are important things considering here that in this particular part, there is some additional readings I have mentioned in this particular slide. So just go through this particular paper. This is link basically. I have mentioned, just go through that particular link. So hopefully this summarizes the exploding gradient problem on an institutional level, because in short, because you are reliving the future further, you go through your network, the power your gradient is, and the harder it is to train the weights, which has domino effects on all of the future weights throughout the network as well. And so how do you come considering this particular vanishing gradient problem? So there is a couple of solutions. For instance, for the exploding the gradient, you can have truncated back propagation. So you stop back propagating after a certain point. But as you can imagine, that's probably not optimal because then you are not updating all the bits, right? But if you don't stop, then you are just going to have a completely irrelevant network. So it's better than the original approach. And then you can have penalties. So you could have the gradient being penalized and being artificially reduced. So you can have gradient clipping. So you could have a maximum limit for the gradient. So you could say never considering this particular part where gradient go over this value, and then if it's over that value, it just stays at that particular value as it propagates further down through network, right? So basically, you have weight initialization where you are smart about how you initialize your weight to minimize the potential for vanishing gradient. So you can have, there are types of networks called eco state network, and considering that part where they are designed to solve the vanishing gradient problem. But there are also a different types of network called long short-term memory network, which is also called as LSTMs for short, which is extremely popular, which are considered to be go through the network for implementing the recurrent neural network. So up to this point, we have seen the concepts of RNN and vanishing gradient descent.